Gas transport number 96 cargo tanks are of double membrane, prismatic type, built in accordance with the IGC code. The tanks have an octagonal transverse section matching with the supporting inner hull and are situated inline from forward to aft. Each tank is located in a hold space formed by two transverse bulkheads. The tanks are equipped to carry LNG at cryogenic temperatures and at a pressure that is marginally higher than atmospheric pressure. They are insulated to reduce cargo loss through natural boil-off. The materials used for the containment system are required to reduce the heat transfer from the hull structure to minimize the boil-off gas from the cargo, as well as to protect the hull structure from the effects of cryogenic temperature. The system ensures that the whole of the cargo hydrostatic loads are transmitted through the membranes and insulation to the inner hull plating of the ship. The function of the membranes is to prevent leakage, while the insulation supports and transmits the loads, in addition to minimizing heat exchange between the cargo and the inner hull. The basis of the membrane philosophy is that, in the event of a leak in the primary barrier, a secondary barrier will contain the cargo indefinitely. Thus, the system has two identical layers of membranes and insulation. These trunk spaces are used for inspection and the passage of electrical cables and various piping systems. The cargo tanks are connected with each other by the liquid, vapor and spray headers, which are located on the trunk space. The nitrogen headers supplying the primary and secondary insulation spaces and other services directly associated with the cargo system are also located on the trunk space. The spaces between the inner hull and outer hull are used for ballast. The ballast tanks will also protect the cargo tanks in the event of an emergency situation such as collision or grounding. The ballast spaces around each cargo tank are divided into port and starboard double-bottom wing tanks, which extend to the side of the cargo tanks as far up as the trunk spaces. In this area, the second and primary insulation boxes are reinforced by thicker internal stiffeners to resist the impacts which may be created by liquid sloshing inside the tanks. It includes the upper part of the tank, including the tank ceilings, and is approximately 30% of the total tank wall surface. Additionally, the primary reinforced boxes have a double top cover. Tank insulation in this area is fitted with normal boxes. It includes the middle and lower part of the tank, including the tank bottom, and is approximately 70% of the total tank wall surface. The port and starboard ballast tanks are separated by a pipe tunnel or pipe duct space extending the full length of the under-tank area. The primary membrane is in contact with cargo. It is thin and flexible as it is made of a 36% nickel steel alloy called Invar and is 0.7 millimeters thick. As the coefficient of thermal expansion of Invar is low, we can use flat sheets instead of corrugated ones. When flat sheets are used, the entire surface area of the membrane is in contact with the supporting insulation. Thus, the load which the system is able to carry is limited only by the load-bearing capacity of the insulation. The primary insulation consists of a layer of plywood boxes filled with perlite, a vitreous rock of volcanic origin. This system allows free circulation of nitrogen and therefore permits gas freeing or inerting to be carried out in the insulation spaces without difficulty. The gaps between the boxes are insulated with a combination of rigid insulating materials and glass wool. The water repellency of the perlite is increased by a silicone treatment. Primary insulation is 230 millimeters thick. The secondary insulation is similar to the primary insulation in construction. It is 300 millimeters thick. The thickness of primary and secondary insulation is governed by the designed boil-off rate of 0.15% of the total cargo tank's volume per day. The secondary membrane, like the primary membrane, is made of flat Invar sheets of 0.7 millimeters thickness. In case of a leak in the primary membrane, it can contain the cargo indefinitely. Further, as it is embedded between the insulation, it reduces the convection currents within the insulation. It is located near the ship's centerline at the aft part of the tank. A stainless steel tripod mast is suspended from the liquid dome. This mast is held in position at the bottom of the tank by a sliding bearing to allow for thermal expansion or contraction depending on the tank environment. The pipes running from the tripod mast pass through liquid dome. Normally, the liquid dome is filled with nitrogen. A gas or vapor dome is located near the geometrical center of each cargo tank ceiling. It has the vapor supply or return line which supplies vapor to the tank when discharging and vents vapor from the tank during loading or venting boil-off. It has 2 spray valves for cooling down purposes and 2 pressure or vacuum relief valves. It also houses the pickup for pressure sensors and the purge line from the discharge pipes of cargo pumps. It consists of the main loading and discharging pipes in the form of a 3-legged trellis structure and is used to support the tank access ladder and other piping and instrumentation equipment. The instrumentation includes temperature and level sensors, high and low level alarm sensors, and cargo pump electric cables. 2 cargo pumps are mounted on the base plate of the tripod mast, and 1 spray pump is mounted on lower support of the tripod mast. Emergency pump column and a float gauge column are also located in the tripod mast. These are submerged electric 2-stage cryogenic centrifugal pumps. 1 pump is installed in each tank. It is used for tank and line cool down, for forced vaporization of cargo, and for stripping the tank. They are started and stopped from the cargo control room. They will be automatically stopped in case of an emergency trip. Normally, this pump is started at approximately 0.7 meters to avoid possible starting problems. These are submerged electric single-stage cryogenic centrifugal pumps. 2 pumps are installed in each tank and used for cargo discharge. They are started and stopped from the cargo control room. They will be automatically stopped in case of an emergency trip. Normally, full discharge rate is maintained until the tank level reaches approximately 0.7 meters, at which time the pump will start to cavitate. The primary membrane is in contact with cargo. It is thin and flexible as it is made of a 36% nickel steel alloy called Invar and is 0.7 millimeters thick. As the coefficient of thermal expansion of Invar is low, we can use flat sheets instead of corrugated ones. When flat sheets are used, the entire surface area of the membrane is in contact with the supporting insulation. Thus, the load which the system is able to carry is limited only by the load-bearing capacity of the insulation. The primary consists of a layer of plywood boxes filled with perlite, a vitreous rock of volcanic origin. This system allows free circulation of nitrogen and therefore permits gas freeing or inerting to be carried out in the insulation spaces without difficulty. The gaps between the boxes are insulated with a combination of rigid insulating materials and glass wool. The water repellency of the perlite is increased by a silicon treatment. Primary insulation is 230 millimeters thick. The secondary membrane, like the primary membrane, is made of flat Invar sheets of 0.7 millimeters thickness. In case of a leak in the primary membrane, it can contain the cargo indefinitely. Further, as it is embedded between the insulation, it reduces the convection currents within the insulation. The secondary insulation is similar to the primary insulation in construction. It is 300 millimeters thick. The thickness of primary and secondary insulation is governed by the designed boil-off rate of 0.15% of the total cargo tank's volume per day. The plywood insulation fabricated are filled with expanded perlite in the form of balls which measure between a few hundredths to a few tenths of a millimeter. The cellular structure so obtained from the process gives to the expanded perlite its lightness and thus its excellent insulation properties. Its water repellency can be increased by a silicon treatment. Treated perlite absorbs about 5% of its dry weight in water, while untreated perlite absorbs far more than 100% of its dry weight in water in the same period. The primary and secondary insulation boxes have lipped Invar tongues stapled along slots running lengthwise. Continuous Invar tongues are positions in the lip of the fixed tongues on the boxes. The membrane strakes are resistance seam welded with these tongues in between. To allow some flexibility, each collar in the primary and secondary insulation boxes is fitted with an elastic coupling. While the collar studs for the primary use a single spring washer, those on the secondary use 3 to 5. These are tightened down on the setting plate for the respective boxes by securing nuts. Boxes on the tank's bottom have a higher number of spring washers because the hull deformation has the largest effect on this area. The primary boxes are secured in position by collar studs. The collar studs are screwed into setting plates, which are also linked to the setting plate for secondary boxes by 2 screws. A plywood wedge is installed between the 2 setting plates to limit any thermal conduction through the box fixations. The plywood boxes forming the secondary insulation are laid on the ship's inner hull through the transition of a flexible plastic-bearing product deposited on the box in the shape of ropes by means of an automatic depositing machine. These ropes are of adjustable thickness and compensate for the flatness defects of the inner hull. Each primary and secondary membrane strake terminates on an invar angle structure 1.5 mm thick, fitted around the perimeter of each transverse bulkhead and welded to it. Due to their superposition, the secondary and primary membranes cross each other in both ways, forming a square tube. With this system, the membranes are directly connected to the inner hull so that any membrane tension is directly and uniformly taken by the ship's structure.